Hello, my name is Kevin Hill. I'm a second semester student at TCAT Chattanooga. Today I'm going to show you how to properly ohm out a split phase motor to identify the run, common, and start terminals. A split phase motor is a motor that has two windings, a run winding and a start winding. First, we're going to need an ohm meter. We'll be using the Fluke 116 ohm meter. First thing you want to do is turn it to ohms, and you want to check your test leads to make sure that they are working, that the meter is working. We have a 0.2 resistance. The next thing that I like to do, I like to draw a diagram of the terminals so as I get the information, the resistance between each terminal, I can record it on my paper. So we're going to come over to the first two leads and we're going to check for resistance. And we get a resistance of 2.8. So we're going to write down the 2.8. We check the next two leads. We'll get a resistance of 0.8. And then we're going to check the last two leads. The last two terminals, last two terminals. We get a resistance of 2. Okay, so now we have 0.8 across these two. We have 0.8 across these two, and we have 2.8 across these two, and we got 2 across these. So the rule is, between run and start, you'll have the highest resistance. So we got 2.8 there. So that tells us that when we check for resistance between these two terminals, we get an ohm reading of 2.8. So the one that you're not touching is automatically going to be the common. Okay, so we can put a C there. So we still have to determine which of these two is run and which is start. So the rule is that between run and start is the highest resistance. The second highest resistance is going to be between start and common. So we got 2 here and we got 0.8 here. So this is the second highest here. So that means that this is start. Therefore, this is run. And when you're checking, when you're ohming to find which terminal is start, run, and common, the values between start and common plus the values between run and common should equal the value between start and run. So we got 2 here, 0.8 here, and we got 2.8 here. So everything checks out. This is good as far as the windings are concerned, and the math comes out correct. So that's how you determine the start, run, and common on a split phase motor. Now the next thing we're going to do, using our ohm meter, we're going to show you how to determine if a motor, a split phase motor, is electrically sound. I'm going to show you how to check it for open windings, short-circuited windings, and ground windings. Okay, this is a good motor, but we're going to go ahead and go through the steps of those 3 tests just to show you. With our ohm meter still in ohms, again, we're going to just make sure that we got good leads here. We got a 0.2, so we're going to become stationary on one terminal, and we're going to check to a metal, to a copper pipe, and we're checking for ground right now. And so we have OL reading, which is a lot of resistance. So it can't, current can't flow. So we're going to go to the next term, OL. And we go to the last term, OL. So this motor is not grounded. So now, using our numbers that we obtained when we were ohming the motor out, the fact that our math came out right with 2 ohms here, 8 ohms there, and a total of 2.8 ohms here, that tells us that we do not have a short-circuited condition. This motor is not short-circuited. And the fact that we have values between the 3 terminals also tells us that the windings are not open, they are intact. Okay, so that's for this particular motor. We're going to go on to another motor. Okay, on this particular motor, we're going to use the terminals, but we're not going to record the values because we're not trying to identify run, common, and start here, but we're going to more so check this motor for open windings, short windings, and short-circuited windings. So what we're going to do, turn our own meter on. Again, we're going to test the leads just to make sure that they're intact. I'm going to go across 2 terminals. So you get a 13.8. We're going to move one test lead and go to another terminal. You get a 3.5. We move the other test lead and go to another terminal. And we get a 3.5. So we got 2 numbers that are exactly the same. So we got 3.5 and 3.5, which is 7. But on the other terminal, we got a 13. So 7, 3 plus 5, and 3.5 and 3.5 equals 7, but we got a value over here of 13, so it didn't equal out. So that tells us that something is going on with the windings in this motor. So the thing about short-circuited windings is whenever that motor begins to run beyond the design specification as far as ampacity is concerned, then the windings will begin to burn the varnish off. See, these windings have varnish on them, and the varnish keeps the path flowing in a circular motion. You know, just the electrons are following the wires. But whenever the varnish is burned off, the electrons will begin to short circuit. They'll take the path of the least resistance. And so that's what short circuited is. So it's not running, the electricity or the electrons is not taking the full path, it's taking a shortcut. And it's short circuited. And that's what's going on with the values that we just recorded from this motor. Now we're going to check it for ground conditions. So there again, we put our terminal, we put our leads on one terminal, and we go to a copper line. You know, it has to be a bare metal place. And we go to a copper line, and if it's not grounded, we should not get a resistance reading. But we get a resistance reading of 21 from that terminal. And we get a resistance reading of 16 from that terminal. And a resistance reading of 3.5 from that terminal. So not only does this motor have a short-circuited condition going on with it, it also is grounded to the casing. So this is a bad motor, and if it was energized, it would really be a dangerous motor. for our last motor that we're going to check, we're going to check for some of the same things. We're not going to identify the run, common, and start, but we are going to check it for ground conditions, open conditions, and short circuit conditions. Okay, between our first two terminals, we get a reading of 109 ohms. We move one lead, and we get an OL. We move the other lead, the next terminal, we get an OL. So what's going on here, we got two windings that are open. You know, perhaps they burn into, but no electrons can flow here. So we're going to go ahead and check it. Check it for ground. And we're getting a reading of 9.8. We're getting an OL reading there. And we're getting a 99 ohm reading there. So not only is there some open windings here in this motor, but it is also shorted. I mean, it's also ground to the casing. So this will conclude our video production, and I hope this would help you in your HVAC endeavors. Thank you.